Thank you, Dr. Chen. It's a great pleasure to give this invited lecture. In this lecture, I would like to talk about another kind of numerical method based on kinetic theory, which is different from the Lett-Boltzmann method, but is closely related to Lett-Boltzmann. Yeah, my talk includes the following 5 parts. First, I would like to give some basic concept about the kinetic theory. And we know that for gas system, we have 4 typical parameters. That's the molecular diameter and the mean molecular distance and the mean free path and domain size. Based on these 4 length scales, we can define a number of dimensionless parameters. And based on these parameters, we can classify the gas system into several different types, such as dilute gas, dense gas, or nano-confined system. Here, I would like to focus on the first type, dilute gas type. And for such system, we only have 1 dimensionless parameter, that's the Newton number, which is the ratio between the mean free path over the domain size. Okay. For gas system, we can describe it at different levels. At the microscopic level, we can use molecular dynamics to track each particle. And at the mesoscopic level, we can use the Boltzmann equation to describe the evolution of the T31 function. And at the macroscopic level, we can just use the Euler equation or Navier equation to describe the whole flow. And based on the Newton number, we can classify a gas flow into 4 discrete flow regimes, such as the continuum, slip, transition, or free molecular regimes. And the Boltzmann equation provides a good basis for describing gas flows involving the different flow regimes. And for Boltzmann equation, it describes the T31 function, which represents the particles at space x, time t, and the particle velocity c. And the hydrodynamic variables such as then mass, moment, and energy can be defined as the moment of the velocity T31 function. And the key point in Boltzmann equation is the collision, term. Yeah, sorry. It doesn't work. So for dilute gas, the collision term is quite complicated. It's actually a 5-fold integration. So usually in practical applications, we just use some relaxing models. The most widely known is the BGK model, which just use the Maxwell T31 function as the target T31 function. But unfortunately, the BGK model, we know that it gives a prompt number 1. And to overcome its limitation, and some advanced models have been proposed, such as the Sharkov model and the ES model. Then these 2 models, the heat flux and the viscous stress, are modified to incorrect the prompt number, different prompt number in the equilibrium dispute function. And by taking the moment of the Boltzmann equation, we can obtain the system of the moment equations. And we can use the Chapman-Enskog approximation to close the moment system. At the 0th order, we can obtain the Euler equations. And at the Navier-Stokes order, we can just obtain a 4th order. It gives the Navier-Stokes equation, and higher orders give the Bonnet or Silber-Bonnet equations. The Boltzmann equation also brings some advantage in design numerical method, even for continuum flows. we can the advantage roots in the decoupling of locality and nonlinearity. As we can see that for the Boltzmann equation, the covariant term is non-local, but is linear. And the coordinate term is non-linear, but local. And for comparison, we can, the Navier-Stokes equation, the covariant term, even in the Euler flux, is non-local and non-linear. This decoupling leads to some advantages. For example, we can treat the flux uniformly, but for classical CFD, we usually treat the Euler flux and the viscous flux in different approaches. And another advantage is that we can treat the flux in numerical flux with a multi-dimensional nature based on the Boltzmann equation, because we can actually construct the flux based on the trajectory of the particle movement. But for classical CFD, we must treat the nonlinear wave propagation. So it's difficult to construct a multi-dimensional numerical flux. So with these advantages, a number of numerical methods have been proposed based on the Boltzmann equation. For example, for rarefied gas flows, there are two types of numerical methods: the discrete velocity method and the Dsfd method. These two methods are widely applied for rarefied gas flows. Another limit for continuum flows, two widely used kinetic schemes are Boltzmann equation for low Mach number flows, typically. But another one is the gas-kinetic schemes, which is designed for compressible flow originally. And for multiscale flows with all Newton numbers, and there are typically two numerical methods. The first one is a unified gas-kinetic method, and another one is the discrete formulation of this kinetic scheme. These two kinetic scheme is related to the gas-kinetic scheme. So now I would like to first give a brief introduction of the original gas-kinetic scheme for continuum flows. The gas-kinetic scheme is actually a finite volume discretization of the Boltzmann equation, but the aim is to solve the Navier-Stokes equation. Here, the moment equation is discretized in time and space with in finite volume formulation, and by integrating this moment equations over a contour volume and within one time step, we can obtain the discrete formulation. And the key is how to construct the flux. For classical CFD, we know that flux F is usually constructed based on hydrodynamic variables. And for example, for one-dimensional case, we can just use the exact Riemann solution to construct the flux at the interface. But in this case, the flux is constructed based on the BGK equation itself. This is based on the formal solution of the BGK equation. Actually, by integrating the Boltzmann equation along a texture line, we can obtain a formal integral solution. We can see that the integral solution actually includes two parts. The first part actually is the equilibrium distribution along at every point and any time along the character line. And the second part is just the distribution function at the starting point. With this information, we can obtain the distribution function just at the CU interface. It also includes these two parts. So now the key is how to obtain the distribution function at the CU interface. The first task is to determine the distribution function at the starting point. This is achieved by using the Chapman-Enskog approximation. We know that in order to solve the Euler equation, we use the zeroth order Chapman-Enskog approximation, and for Navier-Stokes, we just use the first order Chapman-Enskog expansion. And the reconstruction following 4 steps. The first step is based on the CO averaged hydrodynamic variables. We reconstruct the distribution of the hydrodynamic variables in each cell. And this is the first step. We can construct using first order or second order polynomial distribution functions. And then from the reconstruction, we can obtain 2 values at each interface. The L represents the information from the left cell, and another one is from the right cell. So the reconstruction gives 2 values of the hydrodynamic variables on the interface. Another step is then how to determine the distribution function. The distribution function at the cell interface. The two values of the hydrodynamic variables actually gives two equilibrium equilibrium distribution function at the cell interface. Then with these approximations, we can obtain the Chapman-Enskog approximations of the original distribution function like this. We can see that it has a upwind nature. Therefore, the particle velocity brings the left or right information to the interface. And here we have 4 parameters: lowercase a and the capital A and the left and right. So the lowercase a actually represents the slopes of the equilibrium distribution in the cell. And the capital A represents the time derivative of the equilibrium distribution function. Now, the key is how to determine these parameters. We can determine the following 2 ways. The first way is the out-of-bracket expression. Actually, from the expression of the equilibrium distribution function, through the time and the spatial discretization, we can obtain the expressions. Another way is use the moment of. This means that we just express the 2 parameters into a polynomial of the velocity, and the coefficients are determined from the conservation of the distribution function. The result leads to linear systems, and by solving this to linear systems, we can obtain the parameters. And the second task is how to determine the equilibrium distribution function at the cell interface. Previously, we have obtained 2 values of the local distribution function, but they are not identical, and which means that they are discontinuous at the interface. But this G, this G is actually continuous at the interface. We must reconstruct it also. And following the same procedure, we can also just making use of Taylor expansion, and the upwind nature is used again. And so here it also depends on 3 parameters: lower A, capital A, and so on. The construction of these parameters also follow similar procedures. The first one is we obtain the hydrodynamic variables at the cell interface from the previous reconstruct GL and GR. And then by solving the moment system, we can obtain the expressions of the slope. And then we can obtain the time derivative, and by solving another linear system, we can see that the expression is very complicated and contains many parameters. And finally, with the above reconstruction, we can obtain the over different function at the cell interface. And but for smooth flows, these parameters can reduce to the same one. And with the reconstruct different function at the cell interface, we can evaluate the flux and update the conserved variables. Okay, now I give a brief summary of the gas-kinetic scheme. The key point in gas-kinetic scheme is to construct the different function at the cell interface with the formal analytical solution. And this is just the final expression of the reconstruct. And it depends on a number of parameters. Actually, even for one-dimensional flows, we need to determine 21 parameters. And it's very tedious. In one paper, in a review paper about the gas-kinetic scheme, the authors mentioned that he spent weeks of division to give the expression of the parameters, and takes up more than 8 pages. So the GKS is very difficult to analyze, but for coding, it can be implemented step by step. Okay. Now I would like to give to another improvement of the GKS. That's the unified gas-kinetic scheme. We know that GKS is for continuum flows. In order to extend it to multiscale flows beyond the continuum one, the UGKS, unified gas-kinetic scheme, was developed. Thus, UGKS was also based on the formal solution of the BGK equation. But the difference is that for the second part, the original different function now is tracked without using the Chapman-Enskog approximation. But the first part is the same as the gas-kinetic scheme. The final expression of the different function at the cell interface in UGKS is given like this. The first part is the same as GKS, and the second one is tracked by discrete velocity different function itself. And this expression can be proved to satisfy the acyclic preserving property. This means that the UGKS can capture the hydrodynamic behaviors with the finite mesh and mesh size and time step without resolving the kinetic scale. And actually, this property have a clear definition. First, the time step shouldn't be limited by the kinetic reaction time, and the mesh size doesn't need to be limited by the mean free path. And as Newton number approach to zero, that's in the continuum flow. For continuum flow, actually we can show that there's a different function approach to the Chapman-Enskog observation at the Navier-Stokes level. And in another limit, free molecular limit, the reconstruct different function approach the collisionless Boltzmann equation. So actually, this reconstructed different function have the multiscale nature. We can give mathematical proof. Actually, we can by analysis the parameters in the two limit. In two limit, we can prove that the AP properties hold exactly. For boundary conditions in the UGKS, we can use the diffusive boundary condition as in the standard kinetic theory. Okay. Now I would like to give to another multiscale method. That's the discrete unified gas-kinetic scheme. In UGKS, it again rely on the formal analytical solution, and the reconstruction is quite complicated. Actually, if you don't know GKS, it's difficult to code the UGKS because there are still many parameters to be determined. And UGKS is a much simpler and straightforward declaration of the BGK equation. But it has the similar properties of the UGKS. The DUGKS doesn't depend on formal analytical solution, and it's a semi-implicit declaration and implement explicitly, just like the Led-Boson method. And also, we can also show that it has a nice AP property. The starting point of UGKS is also based on the relaxed model. We just integrate the kinetic model over each cell within one time step, and this leads to the following discrete formulation. Now here the time integration is we use the midpoint rho for the convergent term. And for the trapped rho, for the coordinate term, we're using the trapped rho. This gives a semi-implicit one. This can ensure the numerical stability because this term. But this implicit can be removed by introducing two auxiliary different function. This step is actually the same as the Led-Boson method. And so the updating role for the cell center values can be implemented explicitly once the interface, the differential at the interface is known. Now the key is how to determine the differential function at the cell interface. Here we didn't use the formal analytical solution, but we use a character solution. We just integration the kinetic equation along character line, and the coordinate term we also use the trapezoidal rho, and this declaration is also semi-implicit, but we can remove the implicit by introducing another two auxiliary different functions, and so the implement can also be carried out by explicit one. Here, F plus is just represent the posterior collision, at the starting point of the character line. Then we can move the posterior collision different functions along its character line to the interface, and then transfer back to the original one. And from this transfer back, we can obtain the numerical flux. In UGKS, we will only update the different function, but for the hydrodynamic variables, we can obtain it following two ways. The first way is just taking the discrete velocity moment, and another one is we just use the flux method. Actually, we know that if we have obtained the different function at the cell interface, we can obtain the numerical flux, and then we can update the different function, the hydrodynamic variables. Actually, the procedure of the UGKS is similar. First, with the known cell-centered different functions, we can reconstruct the post-collision different function at the starting point of the character line, and then move the post-collision different function to the interface and transform back to obtain the numerical flux. With the numerical flux, we can update the cell-centered different function. So actually, UGKS can be viewed as a semi-Lagrange formulation of the BGK equation, and it uses Euler mesh, but using the Lagrangian evolution for the particle transport. Some main properties will be given here, and the first is uniform stable. This means that the time step is not limited by the related time tau. Actually, the time step is only determined by the CFL condition given by like this. Okay. Another one is that it has the AP properties. We can prove that in the continuum limit, the reconstruct different function follows the Chapman-Enskog expansion as a non-Westock order. This means that in the continuum region, the UGK is actually a non-Westock solver. And in another limit, we can prove that the different function actually is the solution of the correlationless Boltzmann equation. And in the limit, the UGK becomes a Boltzmann solver. Another property is that the different function reconstruct as the interface gives a low numerical dissipation. By comparing the reconstruct the numerical different function and the exact one, we can obtain the error. The error depends on the interpolation accuracy and the time step. The time step appears in the correlation operator. But if we ignore the correlation effect, only consider the transport one, this means that we just use the direct interpolation. This gives that we can see that the time error is relatively large. Here H is the time step. And this feature is particularly useful for flows with a solid wall. In order to capture the boundary layer, this cause boundary layer, we must need a low numerical dissipation scheme. Now we would like to make a comparison between the DUGX and the UGKs. Actually, from the reconstruct different function from both methods share the same structure. We can write out explicitly the difference lies these two parameters, A0 and A1. A0 and A1 for the two methods, they have different formulations. They both depend on the grid Newton number. This alpha is actually the grid Newton number, depending on the grid Newton number. Fortunately, we can see that in the whole flow regime, the two expressions are nearly identical. So it can be expected that UGKs can yield the nearly identical results with the UGKs. Actually, we have found the similar results in our numerical practice. We also compare with the Less-Boltzmann method. Of course, they share some similarities. For example, they both mostly use discrete velocities, and they are both using Euler mesh and Lagrange evolution. And DUGX can be viewed as a finite volume Less-Boltzmann for continuum flows. This is a special case, but some differences are also clear. For example, LBM usually adopts regular unlattice velocities, but for DUGX, we can use both off-lattice or unlattice discrete velocities. For mesh, Less-Boltzmann use regular meshes, and DUGX you can use arbitrary unstructured meshes. And LBM is limited to near continuum flows, and DUGX can be used to flows covering different Newton numbers. And about the Mach number, LBM is usually limited to low Mach numbers, and but DUGX can use the Mach number is not so limited. And another is for steady flows. For steady flows, the LBM is usually converges very slow. But for DUGX, we can use acceleration techniques to improve the convergence. Now, I would like to talk about implementation details of DUGX and give some numerical examples. Actually, the algorithm structure of DUGX is relatively simple because the procedure, the physical picture is clear. The physical picture as explained below. And how to initialize our code? First, we need to give a discrete velocity. And for near continuous smooth flow, we can use the Gauss-Hamilton quadrature, like the net boson method. And for highly non-equilibrium flows, we can use other quadratures to give the discrete velocity. For example, the Newton-Cordes quadratures. And the distribution function should also be initialized. Usually, we can just set its equilibrium. And for more accurate, we can use the Chapman-Enskog optimization or a Hermite expansion. And the other parameters should also be initialized, such as gas properties and the numerical parameters such as mesh and time step. Another detail is how to reconstruct the CO interdistribution. The key is the slope. How to determine slope? We can use some limiters in the reconstruction, such that some unphysical oscillations can be suppressed. And here are some references about the three gas-kinetic schemes. Here are some typical references. We note that some open sources are also available. The first one is realized in open form. This is proposed, developed by Dr. Zhu at our university. And the code can be downloaded at GitHub. And another one is by group from the Stanford University. They released recently. And a sample two-dimensional code is also available at the ResearchGate. Now I would like to give some examples. And the first one is laminar boundary layer. We know that this is critical to test a numerical method. We know that the boundary layer profile is sensitive to measure the accuracy of the numerical method, particularly the dissipation property. And here we just test the laminar boundary layer over flat, and we use non-uniform mesh with different grid resolutions. Here we just compare the velocity profile with the Blasius solution. The results are given by 3 grid meshes, and we can see that even only 3 grid points are within the boundary layer, the results are also quite satisfactory. This is another velocity component is more sensitive, but it shows good agreement with the Blasius solution. This suggests that the DGS is robust and insensitive to the mesh resolution. And here is another test for where the LBM can also be applied. Flow over a square cylinder at the region number 300. And for this flow, from some literature is viewed as the vortex shading is asymmetry, and has a frequency is multiple frequency. And if we use the net boson method with a Cosa mesh, which only obtained a symmetry vortex shading, and the frequency is single. But if we increase the grid resolution to a fine mesh, and we can obtain asymmetry vortex shading and multiple frequency oscillation. But with the DGS on the with the Cosa mesh, we can obtain the axis symmetry, vortex shading, and multiple frequency. This may be due to the properties in capturing the viscous boundary layer. Okay. And another test case is a two-dimensional high marker number reading problem. We just tested 2 cases. One is in the continuum flow. The Newton number is very small. And in this case, the mesh size is much larger than the mean free path, and the time step is much larger than the collision time. And we can see that the result in agreement the Euler solution. And in another limit is the free molecular regime. In this case, we can obtain a net solution from the Boltzmann equation. And we can see that the density, temperature, and the velocity field agree with the analytical solution. This is another test case of high Mach number flow. That's a flow over a cylinder at different Newton numbers. And we measured the heat flux, the pressure, and the stress around the surface of the cylinder and compared the results with the Dsfd data. We can see that good agreement between the results. We also applied the DGS to microflows. The first test case is low speed microcavity flow. We just measured the results at different Newton numbers. The results are in good agreement with Dsfd. And it's particularly interesting for Newton number, this number. Yeah, it's known that at this number, it's believed that non-Stokes Fourier equations can be applied with slip boundary condition. But this is not true. We can see that here is the heat flux. This is a lower temperature, this is a higher temperature. We can see that the heat is transferred from the low temperature region to high temperature region. This means that non-Stokes equation doesn't hold for in the interior region. By adjusting the slip velocity or temperature jump, this can't give the correct result. And in the continuum regime, we also compare the results with some benchmark market data. The results are satisfactory. And another microflow is a microbeam problem. A heated microbeam is put in a cold cavity. And we just test the result, the method with 3 different Newton numbers from slip regime to free molecular regimes. Driven by the temperature gradient, complex vortex appears in every case. And when for Dsfd, it takes a very long time to obtain the average data because a large noise. For the velocity is very weak. We measured the heat flux, stress, and around 8 volts. And compared to the Dsfd data, we can the good agreement can be observed. And the last example is a multiscale problem. In this problem, 2 cavities are connected by a microchannel. The gas chamber is at a normal condition in the left cavity, and on the right cavity is nearly vacuum. So the pressure ratio is very large. This is difficult to simulate because the flow in the left corner is low Mach number and continuum. But the flow in the right cavity is highly rarefied and maybe high Mach number. And so once here we just shows the Mach number at a given time. We can see that the Mach number covers a wide range. And here no vortex can observe, but at a later time we can observe vortex because the flow, the gas is flowing from left to right cavities continuously. Okay, now I would like to give a brief summary. We can see that the GKS gas-kinetic scheme provides an alternative method for classical CFD. And the UGKS and the DUGS provide an efficient source for multiscale flows. And extension to other multiscale transport phenomena such as phototransport, radiation transfer, and electrohydrodynamics. We are now extending this method to these problems. Okay, thank you.
I have questions.
Okay, please.
What about using larger sensors for approximation of distribution functions of the cell's boundaries? What about using more nodes?
More noise?
In approximation of the distribution function from the cell center to the boundaries?
Yeah, we just use now we just use the second slope, just gives a second order, which give a second order accuracy. But if we try to improve to high order, we must use some inner informations. Actually, some people are working to improve the spatial accuracy. Okay.
Solve this problem of different values of distributions going from left to right side.
Yeah. It also follows the particle transition, so it has the upwind nature. At the seal, the particles from left just arrived from the left seal, and the right one will have different values at the seal interface. Okay. Yeah, Professor.
When you consider all these regimes for Knudsen number for light, then you choose the velocity, the discrete velocity that is noticed by this or that version. How do you actually choose the velocity?
Yeah, actually, perhaps this is a common problem for discrete velocity method. For flows with a large Knudsen number, we must give a discrete velocity covering a large wide range, particularly for high Mach numbers. And for highly rarefied gas flow, we also need a large discrete velocity. So the computation cost can be reduced by optimizing the dispersion of the velocity space. Okay, perhaps the self-adaptive particle velocity can be adopted, like the pond. Yeah. Okay.
As the Mach number increases, do you need to increase the number of the discrete velocity set?
Yes. We actually recently we just obtained 26 discrete velocities for three-dimensional computable flows. Yeah, but it's off lattice, not on the lattice. This can be realized to simulate continuum computable flows. Yeah, 26, 27, okay.
Thank you for the method. Is quite interesting. I just wanted to ask if possible to show the references again to take note. Yeah, the page with the reference. The slide with the references.
Oh, the reference, okay.
Yeah.
Reference. Yeah, sorry. I see the reference. Yeah. Okay.
So I have a question about the high Mach number flows. If you do high Mach number flow simulations,
Yeah.
for example, shot structure. And if you use more and more discrete velocities, does your solution get better and better closer to DSMC or no?
For high number flows, actually, we didn't test the grid constant velocity space. Yeah. I think the most expensive part is lies in the velocity digitalization. Yeah. For this, actually, this is a common problem for discrete velocity methods. Okay.
So the cost I understand, but so if you start the simulation at, let's say, Mach 5.
Mach 5, yeah.
For example,
Yeah.
do a simulation in 1D and discrete velocity.
Yeah.
And then you do the simulation again with 50 discrete velocity. Does it get better, closer to DSMC?
Actually, we didn't use different orders because the computing is very expensive. Okay. Okay, thank you.
Question regarding you compare it to LBM, almost you win on every front. All right. So what do you see some disadvantages compared to LBM?
Yeah, it's relatively expensive because for example, we must compute the equilibrium digital function at the cell interface. But for that Boltzmann, we just only compute one time, and we need yeah. So
Cost per time step is much more expensive.
yeah, but fortunately we can use non-uniform mesh. Yeah.
Actually, it's my self-interest. This scheme seems very useful to evaluate what I just proposed.
Yeah, exactly. Yeah, yeah.
Not too deep finance.
Yeah. No,
Might see something
yeah.
that
yeah.
nonlinear Thomas model trying to capture.
Yeah, perhaps we can try using this game to simulate the average kinetic equation. Yeah, yeah. Thank you.